Hello and welcome to section 2.4 on trigonometric derivatives. This video will focus less on derivatives and more on two important trigonometric limit identities. We will end this video with the derivatives of our final building blocks, the trigonometric functions. However, we will not justify the derivatives nor work examples. You will explore them more in class. We begin by proving the identity that sin x over x approaches 1 as x approaches 0. As I warned in section 1.6, the squeeze theorem will be very useful in this proof. Now might be a good time to review section 1.6 and the squeeze theorem. The justification that will be provided in this video for the limit identity differs from our book. To find an alternative proof, see page 142 of Stewart. We will find three functions which bound each other for the squeeze theorem, with the middle function being sin x over x. We'll obtain these functions from taking a circle of radius 1. This shouldn't be a surprise, we are studying trigonometry after all. And choose an angle theta between 0 and pi halves, and use theta to cut a sector from our circle. And then extend the radius until it intersects the line x equals 1. We make these strange choices to obtain three shapes with increasing area: a purple triangle, a blue sector, and a red triangle. The area of the purple triangle is less than the area of the sector, which is less than the area of the red triangle. The three areas are to be used with the squeeze theorem. What are these areas? Let's begin by finding the area of the red triangle. This triangle is a right triangle with an angle theta and an adjacent side, which is the radius of our circle. Therefore, its length is 1. Recall that the area of a triangle is 1/2 base times height. We can see that the base of our triangle has length 1, while the height represents the length of the opposite side of the triangle. We therefore can use trigonometry to find that the height is tangent theta. Therefore, the area of the red triangle is 1/2 times tangent theta. We move to the area of the blue sector. The area of a sector from a circle is 1/2 times the radius of the circle times the angle of the sector. The radius of our circle is 1, therefore the area of the blue sector is 1/2 times theta. We move on to the area of the purple triangle. The area of a triangle is still 1/2 base times height. Our purple triangle is not a right triangle, but we can use trigonometry to find its height. We have a right triangle with angle theta and hypotenuse 1, and we are interested in the opposite length, the triangle's height. Therefore, h is sine theta, and the area of the purple triangle is 1/2 times sine theta. So from the circle, we have found three shapes of increasing area, and from these areas, we have found a string of two inequalities. From the first inequality, if we multiply by 2, we have sine theta is less than theta. And since theta was chosen not to be 0, we can divide by theta to find that sine theta over theta is less than or equal to 1. From our second inequality, we can multiply by 2 to find that theta is less than or equal to tangent of theta. Recall that tangent is the same as sine over cosine. Divide by theta and multiply by cosine, and we have that cosine theta is less than or equal to sine theta over theta. Notice that the direction of the inequality is unchanged, as both cosine theta and theta are positive, due to theta being in the first quadrant. We combine these two observations to obtain our desired squeeze theorem setup. You may not have noticed, but these inequalities hold for an angle theta that is near 0, but positive. Our goal is to find the limit as theta approaches 0, but we only have thought about theta approaching 0 from the right. Rest assured that these inequalities also hold for an angle theta that is near 0, but negative. Therefore, we can use it to find the two-sided limit as theta approaches 0. Cosine is continuous at all points, therefore the limit of cosine as theta goes to 0 is cosine of 0, or 1. Since sine theta over theta is bounded by two functions which both approach 1 as theta goes to 0, sine theta over theta is squeezed to 1. We now have our identity. If you've had trouble following this proof, you can find an alternative proof in Stewart on page 142. We now have a very useful trigonometric identity. In fact, we can use this identity to find the derivative of sin x, and with the derivative of sin x, we can find the derivative of the other 5 trigonometric functions. You won't see that here today, but you will see it in class. Another way the identity of sin x over x is important is in calculating the identity of cosine minus 1 over x as x goes to 0. Pause the video and challenge yourself to justifying this identity. Along with knowing the limit of sine x over x as x goes to 0, you need the identity that sine squared plus cosine squared equals 1, and you should use one of the 4 techniques outlined in section 1.6. Let's narrow our choices of techniques. We cannot directly substitute 0, as we'd be dividing by 0. We cannot simplify any farther, and I don't see any easy squeeze theorem. But I do see a conjugate. The conjugate of cosine x minus 1 is cosine x plus 1. We use the property of the conjugate in the numerator, and don't multiply through the denominator. I mentioned that you would need the identity that sine squared plus cosine squared equals 1. By subtracting 1 and sine squared from both sides, we see that the numerator cosine squared minus 1 is really negative sine squared. You might have gotten to this point and become stuck, but that is okay. We now need to become tricky. Separating the fraction in this way allows us to use our new identity. Remember, we can split the fraction, but we can only split the limit if both limits would exist. From our identity, we know that the first limit would exist and would be 1. While the second function is continuous at x equals 0, so we could use direct substitution. Cosine of 0 is 1, so in the denominator we obtain 2, but sine of 0 is 0, so in the numerator we have 0. In summary, we have 2 important trigonometric limit identities, which we will use in class to calculate the derivative of our remaining building blocks, the trigonometric functions. You should consider these 2 new trigonometric identities as technique 5 among your limit calculation techniques, as they can be used to calculate many trig limits.